Hi there and welcome to this IB biology revision video for lipids, and this is for the IB course from 2023 onwards, and as a reminder, this is not all the content. You would need to revise extra yourself. You cannot rely on this video alone. So first of all, we're going to look at triglycerides, which is an important type of lipid, but weirdly the one that people often forget, and that's because you focus so much on phospholipids linking it to membranes. So before we start, there are a couple of key things that you need to know. So you need to know that the three elements that make up a lipid are carbon, hydrogen and oxygen, except that there's a lot less oxygen now in comparison to carbohydrates that we saw in the previous video. You need to know that there is a difference in saturated and unsaturated, which we will come on to later, which means if it is saturated, there's only single bonds. If it's unsaturated, there are double bonds between at least one of the carbons. You need to know that lipids are have a lower density than water, and they will float on top of water, and you also need to know that lipids are insoluble in water. So if we wanted to dissolve a lipid, we would need to use a different solvent, and the most likely example would be ethanol, which lipid is soluble in. So what do we need to also know about lipids? Well, you need to know there are generally a group of chemicals that are non-polar, okay, which means they are hydrophobic and they don't interact in water. So they'll only dissolve in non-polar solvents such as alcohol or ethanol, as I mentioned before, or ether. They are hydrophobic, and again that means they are attracted to non-polar substances, meaning they are insoluble in water. And the fact that we're going to be looking at triglycerides, we need to just understand why triglycerides are so important. So triglycerides make an excellent store of energy, and that's what they are used in our bodies for. And the reason they make an excellent store of energy is they are chemically stable. So energy is not lost over time. So you can keep it in your body for a long amount of time, and that energy is stored. They're immiscible in water, so because they don't dissolve, they have no osmotic effect, so they won't cause osmosis or lower the water potential. They release up to 2 times more energy than carbohydrates do in respiration, something that we'll cover in the later video. So half of your body mass is actually needed for that, so you could have twice the amount of energy with, in the same amount. So you wouldn't need, say, 10. So there's the same amount of energy in 10 grams of fat as there is in 20 grams of carbohydrates. And they are poor heat conductors, so prevent heat loss. On top of that, triglycerides also have essential roles in protection, so you'll have fatty layers around organs like the kidneys. They are good at insulating, and again the reason that is because they're a poor conductor of heat. So here we have the structure of a triglyceride, and you need to be able to talk about this. It's not that difficult, you just need to be able to make sure you can go through it. So you have glycerol here, which we'll look at its structure in a minute. You do need to know the structure of this, particularly in HL, and you've got 3 fatty acids, hence the name triglyceride. And these bonds here, which we'll look at how they're made, are what we call ester bonds. And you could summarize this structure looking at it like this. Okay, so here is your glycerol molecule, and your hydrocarbon tail is the fatty acid. But let's have a look at that in a bit more detail, because that doesn't make a lot of sense before you look at the whole thing. So triglycerides are made of 1 glycerol and 3 fatty acids, and just as before, we've got this same reaction that we've mentioned in the previous 2 videos about condensation reaction. So if we want to stick a glycerol or bond a glycerol to a fatty acid molecule, it is a condensation reaction. So there's going to be 3 condensation reactions attaching each of the fatty acids to glycerol. So glycerol looks like this. And the way I always remember it is to remember that one side doesn't have any fatty acids attaching to it, so that's this side, which just has hydrogens, but this side here has the OHs, which will allow the condensation reaction to happen, because you need those hydroxyl groups on the one side. The fatty acid molecule has this structure, which is what we're showing you on the previous slide, but didn't make much sense at that point. Okay, so you've got a hydrocarbon tail, which can go on for hundreds and hundreds and hundreds. And this one is saturated because it's got only single bonds. And then at the end of the fatty acid, you have this carboxyl group, I believe, which is C double bond OH, and it's going to be the OH group that is going to combine. So this bit here is going to react with one of these areas here, and that will obviously again be a hydrolysis reaction, leaving one oxygen to link the molecules together. So this is what we have then, where the what's going to bond. So as I said before, you've got the OH groups or the hydroxyl groups on this side of the glycerol, and they're going to react here. So we're going to have a reaction between this molecule and this bit of the molecule. We're going to have a reaction between this OH group and this OH group, and then this one and that one, which will take a H2O away in a condensation reaction to leave water. So 3 condensation reactions. And here you can see they're happening on a simplified form. You're losing the water here, that's going to be removed, and that leaves us with this here, which is your ester bond in fats. Now you need to know the difference between saturated and unsaturated. So here we have a saturated molecule which only has single bonds between the carbon atoms here and here and here in the carbon chain. And because it's saturated, the chain is a straight chain. It doesn't change angles. Whereas in the unsaturated fatty acids, we have these double bonds, and these double bonds cause a kink in the tail. Now that's going to be important when we talk about the fluidity of membranes at a later point. But this kink in the tail means that the unsaturated fatty acids cannot get as close to each other, and that can cause the membranes to be more fluid, or more permeable, maybe a better way to say it actually for the moment. So again, saturated fatty acids, you need to have no double bonds because they're completely saturated, they have no spare bonds, and that is this straight chain as a result. That means at room temperature they are more likely to be solid because the particles are more going to be closer together, acting like particles in a solid. And as an example, saturated chain would look something like that. Unsaturated fatty acids have this double bond, and where there's a double bond, and the term that I'm using is the appropriate term, there is this kink in the tail. That kink means the unsaturated fatty acids are further apart, okay, and that means that they act more as a liquid because they are less likely to be as closely packed together as a solid. And here you can see some examples. So mono unsaturated means we have a single double bond between the carbon atoms, and poly unsaturated means we have more than one double bond. And again, you need to be able to talk about how they combine. So just a different picture here to show you, just to remind you, I think, because it's one of the key points from this video, is that the ester bond here is due to water being removed, okay, and it's between the OH, or the hydroxyl group of the glycerol molecule, and the carboxylic acid group of the fatty acid. Now you need to be able to compare then the structure of triglycerides and phospholipids. So if you look at this, you should just be able to compare and talk about the differences. So if we have a look, they both have glycerol molecules, so they have that in common. The one that people forget to say is that they both have ester bonds, so they are also in common. Now obviously they both have fatty acid chains, but the fatty acid chains are obviously different in numbers. So we have 3 fatty acid chains in a triglyceride, and in a phospholipid we only have 2 fatty acid chains because one of those OHs has been used to attach to the phosphate group instead. So if we're looking at phospholipids, you need to be able to describe their sort of structure again, and you could say that they are made of a phosphate head, which is hydrophilic. It is water loving, so that is the phosphate head in this version here. Apart from in real life, it sort of bends and twists the glycerol, so it comes out to the front, as you can see here. Okay, so the hydrophilic phosphate head, whereas we have a hydrophobic phosphate tail, fatty acid tail, sorry. So the tail is obviously hydrophobic, and you might see a more simplified version here, as you will in the membrane later on when you're studying it. So the uses of phospholipids, they may be saturated or unsaturated. Okay, they may allow the control of membrane fluidity, and in colder climates they might have more unsaturated phospholipids to ensure that they will have fluidity even though there's low temperatures. So what else do we need to know then about lipids? Well, we need to know that we can obviously hydrolyze the ester bonds. That will break down the glycerol and fatty acids, and that can then be used in respiration. And we can completely break down phospholipids to water if you think about the fact they've got lots of hydrogen molecules in there and in carbon dioxide to make energy as ATP. Respiration of 1 gram of lipids, as I said earlier on, will give us twice the amount of energy of carbohydrates, and we also said about them being insoluble. Now, one area that you need to know about, and we will look at phospholipids again when we come back to membranes. So if you want to look more at phospholipids, please look at the membrane video. But one area that you need to be aware of in a small amount, but definitely be aware of, is steroids. And basically, there is steroids, obviously, you will have heard of, but they are effectively often a type of hormone. And steroids can pass directly through the phospholipid bilayer. And that is because the phospholipid bilayer is lipid soluble, so what it means is it allows lipids through, and steroids are non-polar again, so they are water hydrophobic and they will pass through the membrane. You need to know that steroids have the following features. They have 4 fused carbon rings. So here, if we have a look at this one, corticosterone, this one has 1 ring there, 1 ring there, 1 ring there, and 1 ring there. So 4 rings, okay, of carbon. Now within these 4 rings, we have 3 rings that are cyclohexane rings. So we've got here 1, 2, and 3, and then 1 which is a cyclopentane ring. Okay, so that's that one there. And the whole steroid molecule has 17 carbons in total. So important for you to learn those key facts. Now, an example of a steroid hormone is cholesterol. And cholesterol, again, you'll look at much more in the membrane module. But you need to understand that cholesterol is a steroid. It is not made, therefore, of glycerol and fatty acids. It is made up of 4 carbon rings. And again, as we just said, the properties we just mentioned a second ago. And what the steroid molecule does is it sits between the phospholipid tails in the phospholipid membrane, so there's one there, okay, and it will regulate the fluidity and strength of the membrane. And again, we'll have a look at how it does that in the membranes video. But just important that you're aware of it. Cholesterol often people associate as a bad thing, but it's an essential part of your membranes regulating the fluidity and strength of the membrane.